Okay, so from the demo, I hope that this is what you've understood. That as the distance, so down here we get as the distance between the two distributions gets further and further apart. So as we increase the mean of the diet, the power goes up. And that's what this curve shows us. This is called the power curve. So it tells us that the power goes up as we get further and further away. So from the null. So you can see if there's a small difference between the null and the diet, we're not going to have very much power to detect the difference. So if the rat comes from a population whose mean is 140, we will be down here somewhere, say the 140, we will have, maybe a 90% power of detecting a rat on the heavier diet. Okay, so that's the power curve. And the conclusion we can, in summary, the conclusion we can come up with is that the power increases as the two populations means become further apart. Or we can say as delta increases, where delta is the distance between them. And if you think about this makes a lot of sense, that if the diet that the flab rat is on is going to make them that much heavier, then it's going to be that much easier to distinguish from the flab rat who's not on the diet. That's all this says. So the power increases as the delta increases. All of that holding alpha constant. Okay, so what's causing this problem? We see that when they are far apart, then we've got very good power. That's what we've just said. Whereas when, and this was the plus 100 diet, whereas going back to the plus 50, we see that there was more overlap. And so the plus 50 caused us more problems because it gave us less power because of the overlap. Now, are we stuck with this? Is this where we're always going to be stuck? And, well, maybe there's another way of overcoming this. So this curve has a mean of 100, and this one had a mean of 150. All right. Now, what if? How else can we cause the overlap to go down? We can keep the means where they are, but if we can lower the standard deviations. So, for example, this curve on the left, if we made it with a smaller standard deviation, we would get something that looks something like this. Remember, the area has to be 1, and so it has to go up a little bit. It might look something like that. And then the green curve, we do the same thing for the green curve. And then look what happens. Here's the overlap. The overlap is just this. If the green curve would then do something like that. If we could retain the means, so we could keep them on the same diet, but lower the standard deviations, then the overlap goes from this much all the way down to this much. How can we achieve this? How can we achieve this? Well, let's think back to the central limit theorem. So the central limit theorem tells us that as the sample size goes up, the standard deviation or the standard error goes down. So in terms of our flab rats, if instead of finding one flab rat out in the hallway, we found 2 flab rats out, then we might say, whoa, wait a minute, what do I do now? Well, I can weigh them individually, just like we did before, but assuming that they both came from the same lab, what I can do is I can take their average. And then I need, as my distributions to look at, I need to look at the distributions of the sample means. And that's what the central limit theorem lets us do. In fact, if the dotted ones refer to a sample of size 2, then their standard deviation would be sigma over the square root of 2. And the same here. It would be another sigma, of course, but it would be sigma over the square root of 2. So that would be tighter. So go off and try the demo and see what effect the sample size, by increasing sample size, what effect that has on your power.